Hello my schoolers, you welcome to my school YouTube channel. My name is Emmanuel, and in today's video we'll be tackling JAMB CBT past question for the year 2024 in chemistry. Please don't go anywhere, stick around and we'll be right back. You're welcome back to my school YouTube channel. Like I said earlier on, today we'll be looking at JAMB CBT past question for chemistry in the year 2024. Today we'll be looking at question 76 to 100. Now let's get down to the first question 76. The IUPAC nomenclature of the complex K4FeCN6 is what? We have potassium hexacyanurate 2, potassium hexacyanurate 3, potassium hexacyanurate 4, ferrite 4, potassium hexacyanurate 6. You discover that the only thing that is different here is just the 2, 3, 4, and 6. Okay, every other thing we have potassium hexacyanurate. So what the examiner actually wants you to do is to know if you can actually calculate the oxidation state of iron, which is the ferrite. Okay, because that's the only thing that we have different here. So we have potassium hexa, that's 6, cyano, okay, ferrite, of course, from your ferrous, okay, ferrite, what is it? So we can only do that by calculating our oxidation number, oxidation state of Fe, which is iron, in the compound. So let's move on to the board so that we can do justice to that. So we have K4, we have Fe, okay, that's the ferrite, then we have Cn in the bracket 6 of that, okay. So we equate this to be 0 equal to 0, and then we know that potassium is actually positive 1, so plus 4 plus 1, but we have times 4 there, so we have it 4 times, okay. Then we have plus Fe, that's the oxidation number we had to find, then plus cyanide is actually minus 1, okay, cyanide, then we have times 6 of that, okay, that will be equal to 0. So this will be positive 4 plus Fe plus times minus is minus 1 times 6, that is 6, equal to 0, okay. So we have Fe will be negative 6 plus 4 equal to 0. So that is Fe plus minus 6 plus 4 gives us minus 2 equal to 0. So which means Fe is actually 2, positive 2, okay. So that means this is ferrite 2, okay, ferrite 2. So let's move back to the screen and see the IUPAC nomenclature of the complex. This K4FeCN6 is what? So we have ferrite is actually 2, so which is 2 here. So we can call it now potassium hexacyanurate 2, not 3, not 4, not 6. So the correct answer here is option A. Question 77. An example of an amphoteric oxide is what? What amphoteric oxide? Amphoteric oxides are oxides of metals. Okay, remember we talked about acid and hydride. Acid and hydrides are oxides of non-metals, okay? But amphoteric oxides are oxides of metals that can act as an acid in a reaction, and they can also act as a base in a reaction. So they have a dual identity, okay? They can act as an acid to form salts and water. They can also act with base. They can react with base to, form salts and water too, okay? So out of all of this, we have P4O10, we have Al2O3, we have CuO, we have K2O. Among all of this one now, of course, this is the metal. Phosphorus is not a metal, so this is not phosphorus oxide. So this one is eliminated. This one is metal, this is metal, this is metal, okay? But among them here, the oxides of zinc, okay, like zinc oxide, lead oxide, okay, aluminum oxides are amphoteric oxides, okay, because they can act as acid and act as base. So Al2O3 is the correct answer. Let's look at what happens. Al2O3, okay, Al2O3, we said it can react with an acid. So let's have HCl here, okay. If you have this, we have Al, we have AlCl be formed, okay, that's AlCl3, and then we have that's the salt, and this is the water, okay. We can balance this equation. Here we have 2 here because aluminum is 2 here, then this one will be 2 times 3, that's chloride is 6. So this is just, so we can have 6 here. And then we have water, hydrogen will be 6 here, hydrogen is 2 here, so we can have 3 here. So the equation is balanced: 6 moles of hydrogen, 6 moles of chlorine, then 2 moles of aluminium, then oxygen is actually 3 here. So this is balanced. So this is your salt and this is your water, okay? So the same oxide of this aluminium can still react with a base, just as this, and still form salt and water, okay? So we are going to have sodium, okay, Al, then we have O2 be formed here, then we have plus H2O. So we can balance up this. This is the salt we are going to have here. Sodium, aluminium is 2 here, aluminium is 1 here, so we have 2 here, okay, that balances. Sodium is now, oxygen is 4 here, okay, sodium is 2 now, sodium is 1 here, so we can have 2 here. Let's see. Oxygen will now be 3 here, oxygen is 6, that's 4 plus 1, 5. Okay, let's have, that will be 5. Then oxygen here is 3. Oxygen here is 2. Okay, that's 5. Okay. Then hydrogen is 2. Hydrogen is 2. I think the equation is balanced. Now, aluminium is 2 here. Aluminium is 2. Okay, so these are salts here, and then these are water. So you can see that aluminium oxide actually reacts with acid to form salt and water. The same aluminium oxide reacts with sodium hydroxide to form salt and what? And water. So this makes this what? Amphoteric. Okay, so let's move back to the screen and see an example of an amphoteric oxide. Remember, amphoteric oxides are oxides of metals that can act as acid and base in the reaction. So the correct answer here is option B, aluminium oxide. Question 78. The firm that is not associated with petroleum industry is what? The term that is not associated with petroleum industry is what? We have cracking, we have saponification, we have polymerization, we have fermentation. I think this is a bonus mark, but let's see. Cracking has to do with, we have a large, hydrocarbon, okay, compound that is splitted, that is broken down. It could be through catalyst, use of catalyst, okay, like catalytic cracking, okay, and then we can have thermal cracking too. Thermal cracking, we can use heat, apply heat. So in this case, when you have a large or a big petroleum product, okay, you can split it. It can be broken down into more useful and simpler or lighter, hydrocarbons that will be used. For instance, crude oil, okay, in the raw state of petroleum can be splitted into their different fractions. Through fractional distillation, we have petrol, we can form petrol, we can form kerosene, we can form bitumen, we can form every other product of petroleum, okay, can be fine. So cracking is actually associated with petroleum. Option B says saponification. Saponification has to do with conversion of fats and oil, reacting it with alkali, okay, to form soap. This is your process of making soap. Actually, directly, it might not be, but it is a process that is used in testing, okay, carrying out tests. When we want to carry out analysis on petroleum, we use this process to carry out analysis. So this is also associated with petroleum. Option C, polymerization. When we have, gases, okay, of smaller molecule, okay, we can add them up together, or we can join them together, we can bind them together to form a larger, desirable molecule, okay? That's what we call polymerization. So this is also applicable or associated to petroleum. The last option here, fermentation. Fermentation has to do with breaking down process, okay, of carbohydrates or of food, okay, by microorganism. Usually the microorganism could be yeast, okay, because yeast is a microorganism that helps, to break down sugar, okay, into alcohol, and then we have carbon dioxide is given off eventually, okay. So like in the breweries, okay, where drink is made, fermentation is useful there. If you talk of industries where bread, okay, and those snacks are made, they make use of fermentation process associated them, but not to petroleum. So based on that, the correct answer here is option D, fermentation. Question 79. Kerosene is used as solvent for what? Don't forget that kerosene is one of the fractions of petroleum, okay? So kerosene is used as solvent for what? We have paints, we have sulfur, we have gums, we have fat. Don't forget, solvents, usually they will dissolve the substance, okay, that you are having into. So most cases where paints get stronger or harder, okay, maybe you've exposed this to air, you freeze it, and then it's tougher, you can add kerosene to it to act as a solvent, so that it can act as a thinner. Okay, we call it thin, to thin that paint. Okay, once it does that, it will make it so when you apply that paint on the substrate or on the surface, it can it begins to shine, and then it can appear more on it. So not for sulfur, not for gums, not for fats. Yes, kerosene could be used to dissolve fats and oil usually, okay, in some cases, okay, but it finds more application with paints, okay, than when we have it in fat. So based on that, kerosene is used as solvent for paint. So the correct answer is option A. Now let's move on to question number 80. A typical chemical reaction will be spontaneous if what? When we talk about spontaneity of a reaction, it means that the reaction can actually take place, on its own without any external source of energy to apply to it. So a typical chemical reaction will be spontaneous, can be rapid, can take place on its own if what? Enthalpy change is negative, free energy change is greater than 1, entropy change is 0, enthalpy and free energy change are equal. Now there are three conditions for spontaneity, okay, of the spontaneous of a reaction. I'm going to mention them. Okay, the first one is that your delta H must be negative. Okay, I'll write that on the board. Delta H must be negative. Delta G must be negative. Delta S must be positive. Please take note of this for you to look at, because sometimes they will not ask you. It is very common to ask for the value of delta G. Is it positive, is it negative for a spontaneous reaction? But take note of these three. For a reaction to be spontaneous, delta H, which is change in enthalpy, okay, the amount of heat, the internal heat energy that is needed for that reaction to take place, must be negative. That means it must be lesser than 0, okay? Because if it is equal to 0, that means that equilibrium. Then delta G must be negative also. Delta G is your change in free energy, okay? Which must be negative because you need that reaction to take place on. So it must not be equal to 0. If it is equal to 0, that means it is at equilibrium. If it is greater, if it is positive, it means it is greater than 0, and that will mean that it is non-spontaneous. It will still require then delta S, which is change in entropy, okay, talking about the level of disorderliness, okay, in that system, must definitely be what? Be positive. So we have delta H, which is change in enthalpy, must be negative. Change in free energy must be negative also, but change in entropy should be positive. So let's move on to the screen and see. Option A says enthalpy change is negative, which is delta H. Okay, it's negative, that is correct. Option B says free energy change is greater than 1. If free energy change, that's delta G, is greater than 1, it means that it will be positive, because delta G should be negative, means it will go below 0. Okay, but if it is greater than 1, it means that it's actually what? It's positive. So this is not correct. Option C says entropy change is 0. If entropy change is 0, that means delta S is 0. That means it is actually, okay, at equilibrium. It is not positive. But option D says, so this is not so correct. Option D says enthalpy and free energy change are equal. If enthalpy, that is H, and then G, if they are equal, of course, it also means that it is not, because we are saying that the heat that is needed and the free energy, they are equal. So this also is not correct. Okay, so the correct answer here is a typical chemical reaction will be spontaneous if enthalpy change or delta H is negative. Okay, so the correct answer is option A. Let's move on to question number 81. The indicator used in a titration between strong acid and weak base is what? Remember that an indicator is a substance that is added, okay, to either an acid or a base to check for the what? For the pH, for the acidity or the alkalinity of that particular solution, okay, if it is acidic or if it's base. And that will happen by what? A color change. We can know that by color change. Like your litmus paper is an example of indicator, because if you bring a blue litmus paper into an acid, it changes the color to red, or the red litmus paper, if you bring it to a base, it changes the color to blue. Okay, so that's an indicator. So we have other indicators like the methyl orange, like we can have it here. We have methyl orange, we have phenolphthalein, we have bromothymol blue, we have bromothymol red, we have methyl red, and so on and so forth. We have so many of them. they have their different characteristics, okay? When you are reacting a strong acid with a strong base, there's a specific indicator that will work. If you are reacting a strong base with a weak acid, there's a kind of indicator you can use. If you are reacting a strong acid with a strong base, there's a kind of indicator you can use to effect the color change that you so desire, okay? But in this case now, the question is, the indicator used in the titration between strong acid and weak base is what? We have methyl orange, we have phenolphthalein, we have bromomethyl blue, we have methyl red. The correct answer is methyl orange. Methyl orange, when you react strong acid with weak base, okay, you have methyl orange. Can be, even if you react a strong acid with a strong base, you can still use methyl orange, okay? But if you are reacting, now take note, react strong acid with strong base, you can use methyl orange. If you are reacting strong acid with weak base, you can still use methyl orange. But if you are reacting strong base with weak acid, what you need to use is phenolphthalein. That's where phenolphthalein comes in. So phenolphthalein indicator is useful when you are reacting a weak acid, yes, with a strong base, okay? You use phenolphthalein, okay? Then bromomethyl blue, you can use it if you are reacting a weak acid with a weak base. Sometimes it could just be change in concentration that would increase that, okay? So you can still use this for a weak base and weak acid. So let's move on to the correct answer now. The correct answer, for the sake of this question, the indicator used in titration between strong acid and weak base is methyl orange. So the correct answer is option A. Now question 82. Nitrogen obtained from air is not absolutely pure because it contains the following, except nitrogen obtained from air. Don't forget that air, like we defined, is a mixture of gases. So because it is a mixture, it is impure, okay? So we can separate each of the components of those gases into their components by fractional distillation. Where we talk about fractional distillation of air, liquefying the air, okay? So, but nitrogen actually does not support burning. So if there's going to be any other gas or any other substance, part of the air that will make this nitrogen impure, we also act like it, like in terms of not supporting burning, okay? Oxygen supports burning, okay? That's why reactions can take place in the presence of oxygen. Combustion reaction, okay, can take place because oxygen supports burning. Carbon dioxide does not support burning. That is why it is used in the manufacturing of fire extinguishers that we have carbon dioxide. Inert gases like argon also do not support burning, okay? We have water vapor also does not support burning, okay, like we have in this. So these three do not support burning. Carbon dioxide does not support it, inert gases does not support it, and then water vapor does not also support burning, but oxygen support burning. So nitrogen obtained from air is not absolutely pure because it contains the following: carbon dioxide, inert gases, water vapor, except oxygen. So the correct answer is option A. Question number 83. Solubility curve is a plot of solubility against what? Okay, if you are familiar with a solubility curve, don't forget solubility has to do with the amount of a solute, okay, that is dissolved in 1 dm cube of solvent. Dissolved in 1 dm cube of solvent, but it is actually a condition that it must be with a given temperature, okay? Different temperatures can determine to a greater extent the level of solubility, okay? So that is why solubility curve, usually on the y-axis we have solubility on the y-axis, and then on the x-axis we have the temperature, usually will be what the curve is all about. So solubility curve is a plot of solubility against temperature, not pressure, not volume, not concentrate. It is against temperature. So the correct answer is option A. Question number 84. If 11 grams of a gas occupies 5.6 dm cube at STP, standard temperature and pressure, calculate its vapor density, given that 1 mole of a gas occupies 22.4 dm cube. So this is just a simple proportion, okay? We don't know the gas, okay, but we're given the mass of that gas. So 11 grams of a gas occupies 5.6 dm cube, okay? Let's move on to the board and solve that. 11 gram of gas, okay? 11 gram occupies 5.6 dm cube, okay, of the gas. 5.6 dm cube of the gas at standard temperature pressure. So if 11 gram occupies 5.6 gram of that, what mass, okay, of gas will occupy 22.4 dm cube? That is what the question says, okay? So if 11 gram occupies 5.6 dm cube, how many, what quantity of mass of that gas will occupy 22? Because it is at STP, standard temperature and pressure. Because it's at standard temperature and pressure, we are going to determine the mass of what is going to be at standard temperature and pressure. So what we have is, we have 11 gram gives 5.6, and then x gram will give 22.4. So when we cross multiply, we have 5.6x is actually equal to 11 times 22.4. So we divide both sides by 5.6, divide both sides by 5.6. So we have x is going to, by the time you punch into your calculator, 11 times 22.4 divided by 5.6 is going to give us 44, okay? It's going to give us 44 gram. That's what we're going to have, okay? But the question says we should find the vapor density. So this that we have here now is actually the molecular mass, or the mass, okay? Molecular mass of the gas. We obtained it to be 44 gram. But don't also forget that there's a relationship between molecular mass and vapor density, because we are asked to find the vapor density. But what we calculated was the mass. So we can say molecular mass is actually equal to 2 times vapor density. Is equal to 2 times vapor density. So we can say molecular mass, already we had that to be 44. We substitute that here, equal to 2 times vapor density, okay? So which means we're dividing both sides by 2. Vapor density will be equal to 44 over 2. That should be 22 gram, okay? No, it does not have that. It's vapor density, okay? So that's 22. So if you look at it, we have 44 here, you have 22 here. So you have to be careful, because it's possible you could have the two answers. Let's look at the screen, okay? Option A says 22, like we had. Option B says 44. So if you had gotten just related, if 11 gram occupies 5.6, then x occupied 22.4, you would have had 44, and then you stop there. And then, so the answer is actually there, is B, and then you will choose that, not knowing that you still need to what? Calculate for the vapor density, because there's a relationship between molecular mass and vapor density. Vapor density times 2 gives us molecular mass. So what we had here, which was 44, you have to equate it to be 2 times vapor density to eventually have 22. So the correct answer is option A. Do you know you can actually take practice questions on our simulated JAMB CBT past questions? All you need to do is to click on the link in the description below that takes you to the Myschool website. There, you'll be able to download the Myschool mobile app for your Androids and the Myschool software for your computers and laptops. Please go ahead and start practicing. Now, let's move on to question number 85. The van der Waals forces of attraction operates between atoms, cations, molecules, and anions. This is actually molecules. Now, the van der Waals forces of attraction operates between molecules that are close to themselves, okay? It could be between, polar solvents or polar molecules of, permanent dipoles that have opposite dipoles, or it could be between those ones that have dipolar, okay, that are of molecules that have polar solvents, polar molecules, okay, that are dipolar, okay, maybe they are positive, or that are either they are permanent or they are not. So the van der Waals force of attraction usually operates between molecules, not anions, not cations, okay, and not atoms. It is usually among molecules. So the correct answer here is option C, molecules. I hope you enjoyed this content. If yes, please don't forget to click on the like button, hit the subscribe button, and finally tap on the notification bell to keep you informed once we upload our next video. Now let's move on to question number 86. The electronic configuration of an atom of nitrogen is 1s2, 2s2, 2p1x, 2p1y, 2p1z. Because the atom is, option A says, is an excited state. Is in an excited state. Is in an excited state? No, that is not the reason why the electronic configuration is written this way. Okay, the excited state will show that electron has moved from the ground state, okay, either by absorbing or what, or releasing energy, but this does not show that. So option A is not the answer. Option B says undergoing energy changes. Undergoing energy, if it's undergoing energy changes, that means we are talking about the change in enthalpy, okay, but this really will not show, does not really depict that it is undergoing energy change. Option C says the unstable and ready to combine, okay, because the atom is unstable and ready to combine with another. If it is unstable and ready to combine with another, so I think we should have it as 2. Maybe we have it, the first shell, what it should have, then the outermost shell, what we should have there. So this does not show that it is unstable and ready to combine with another one. But option D says simply obeying rules governing electron configuration. Yes, simply obeying the rules governing electronic configuration. If you look at this, we have 1s2, 2s2. So we have each of them are, this one is a lower energy orbital to this. So first of all, the three rules that govern electronic configuration, we have the Aufbau principle, we have the Pauli exclusion principle, and then we have the Hund's rule. Okay, now we have the first orbital, okay, is filled first before the other one. That is the Aufbau principle that says that the lower orbitals are first filled first. We're trying to what? Fill electrons. So this shows it. Then the second one, which is Pauli exclusion principle, that one states that no two electrons can have the same number of quantum number, or the same quantum number value for quantum number at the same time. No two electrons can have the same value for all the 4 quantum numbers at the same time. We talk about the principle, we talk about the azimuthal, we talk about the magnetic, we talk about the spin. It is not possible to have that. That is what is happening here. Okay, then option the third one actually talks about the Hund's rule that says that in trying to fill each of the orbitals, okay, electrons in orbitals, you will fill each of them singly first. One electron will enter each of the orbitals first, which is what we see here. One is entering the p first, one here. So we have 3 for this orbital, 2p, this is 2p3 for nitrogen. Don't forget, this is 1s2, 2s2, should have been 2p3 because it has atomic number of 7, okay. So, but we cannot say, instead of, if Hund's rule is not being obeyed here, we would have had, instead of these 3 here, we would have had 2 for this, then we have 1 here, then this would have been 0. But you must fill each of the orbitals first, 1 and 1. Then we have, for another element, the second electron comes in here in the opposite direction and it is splitted at that point. So the electron configuration of an atom of nitrogen is what it is now because the atom is simply obeying rules governing electron configuration. So the correct answer is option D. Question number 87. The reaction of hydrogen and chlorine to produce hydrogen chloride gas is explosive in what? Is it diffused light? Is it sunlight? Is it infrared light? Is it Raman light? Raman light, diffused light are types of light that are formed when there is scattering of light, either scattering or absorption of light, okay? But for this sunlight is, of course, like we know, it's a natural light from the sun, what we call the solar, energy that we got from it. Now, the reaction of hydrogen and chlorine has to do with what we call a free radical reaction, okay, where there is protonation taking place, okay, between hydrogen and chlorine. So the only kind of light that can make that reaction to take place is what we call the sunlight. So now what happens is that if that reaction takes place under the presence or during the presence of sunlight, there is usually what we call explosion. It can lead to explosion, okay? So under certain condition, when hydrogen and chlorine reacted together to form hydrogen chloride, which is gas, it takes place, or that reaction is only possible in the presence of sunlight. So as a result of that, the reaction of hydrogen and chlorine to produce hydrogen chloride gas is explosive in the presence of sunlight. So the correct answer is option B, sunlight. Question number 88. The term strong and weak acids is used to indicate what? Indicate the what? The number of hydrogen ion released by an acid, the number of hydroxyl ion released by an acid, extent of ionization of an acid, strength of its action on substance. When we say strong acid and weak acid, strong acids actually are acids that dissociate completely, okay, when dissolved in water or in solution. They dissociate completely. For instance, HCl. If you dissociate HCl, we are going to have H positive plus Cl minus. The hydrogen ion dissociates, separates completely, okay, from this. So this is a strong acid, okay. But weak acids are acids that dissociate partially, okay. They dissociate partially when dissolved in water. When they come in contact, for instance, the common one, the acetic acid, that's ethylic acid, CH, yeah, okay. If you have this, you are going to have H plus, then plus we have CH3, COO minus, okay. So we still have hydrogen in here, okay. All the hydrogen that are present here that makes it an acid actually are not dissociated. They are partially. Only this hydrogen is dissociated, while we still have hydrogen, 3 hydrogen in this, okay, to make it. So this becomes what? A weak acid, because there's partial dissociation while this one remains strong. And when we talk about partial or complete dissociation, it's talking about the extent to which there is ionization, okay. There's ionization in this place. The extent which is, okay, it says is used to indicate the number of hydrogen ion released by an acid that is dissociated by an acid, okay, that is separated would have been, because but because the number of hydrogen ion released by an acid, we can have this. That does not determine. In a way, it's looking correct, but it's going to be depending more. It is likely spelled out compared to extent of ionization of an acid. When you talk about extent of ionization of an acid, we are talking about how much of the hydrogen is being able to dissociate, okay. When a metal is coming in this, for example, how many is able to be displaced, okay. So we talk about how many hydrogen can be displaced. Of course, we talk about basicity of an acid, the strength of an acid, okay. So the extent of ionization, the number of hydroxyl ion released by an acid, this is not applicable, because number of hydroxyl ion released by an acid will not be, because this should be for what? For a base. And then extent of ionization of an acid, the strength of its action on a substance. Yes, the strength of its action on a substance can determine if it is strong or if it's also weak, okay. Yes, this is correct, but this is all encompassing, okay. This one can cover up for option D and also for option A. This one is eliminated. So that is why we will go for extent of ionization of an acid, which is also talking about the level of dissociation, okay, of the hydrogen ion when it is dissolved in water or in a solution. As a result, the correct answer is option C, extent of ionization of an acid. Question number 89. The main constituent of water glass is what? Water glass. Of course, glass is one of the products that you can have as a silicate, okay? Silicate, like we have SiO2, okay? Okay, so when we talk about water glass is a solid glass that is made from, of course, we also call this, water glass is also called sodium silicate, okay. I think this will just help us with the answer. Sodium silicate is the other name that is, but don't forget that glass has about SiO2, that's about 78%, okay, of SiO2, silicon dioxide, okay. That is your sand, okay, that use all the glasses, most of the glasses that are made, the bottles in the breweries that are used in the pharmaceutical company, they have a larger percentage of them made from sand, okay. So we have, that's the silicate aspect, the silica aspect, that is this. Then we have sodium also. So the sodium aspect of this water gas is what we call sodium oxide, okay. Sodium oxide that we have is Na2O, okay. Sodium oxide reacts with silicon 4 oxide or silicon dioxide to give us what we call water glass, okay. So based on this, option A says calcium silicate 4, yeah, calcium, because we have calcium carbonate, which is limestone that is used in making glass, that is ordinary glass, but not water glass. Okay, that is why this will not be correct. Option B says calcium triosulfate 4. No. We have sodium triosulfate 4. Okay, it's not a sulfate salt, that is it is a triosilicate. So option B and C are eliminated. So the correct answer should be between option A and option D. But like we said earlier on, that water glass has another name that is called to be sodium silicate. Sodium silicate, sodium oxide, sodium from sodium oxide, and then the silicate from your what? Silicon 4 oxide or silicon dioxide. So which means that this is the silicate here, and then we have the sodium. So of course, if you had mixed this together, we should have had, we have SiO2 plus 1, that's O3, so we can have Na2SiO3. So this should be the formula for the water glass. So we have sodium trioxosilicate 4. Sodium trioxosilicate 4. So the correct answer is option D. Question 90. Which of the following represents an order of increasing reactivity? Talking about reactivity of the metals, of elements, how do they have? We have a series that we use. So which of the following represents an order of increasing reactivity? AU less than CU less than SN less than this, and blah blah blah. So before we answer this question, there is a mnemonic usually that I use, okay, that's been helping me to help me align and then arrange the metals, okay, or the elements in order of reactivity. That's a series what I use. So let's move to the board so that we can see. Okay, the mnemonic I use usually is play soft, like, you know, like choir master. Maybe there's an instrument you want to play, like a keyboard, like a piano. Okay, so play soft, like choir master always zealously introduces tunes and leads hymns and chorus slowly, gently, and passionately. Okay, I can say that again. Play soft, like choir master always zealously introduces tunes and leads hymns and choruses slowly, gently, and passionately. So if we have that, each of those ones, now each of those letters, now you can recite it as much as you can so that it can help you until it sticks there. Okay, so the P actually stands for potassium, the S stands for sodium. Okay, to help you, we have about 2 S's here. We have one S here, one S here. We have C here, and that's C here. But the one, so that you don't mistake one for the other one, you know that this one is possibly in group 1. Group 1, okay, so group 1, can you see that now? This is group 2, group 2, group 3. Can you see that? So before you begin to talk about the rest, okay, so P is potassium, S is sodium, L is lithium, C is calcium, M is magnesium, A is aluminium, Z is zinc, I is iron, T is tin, L is your lead, then H is your hydrogen. Yes, hydrogen is not a metal, but you know it's in group 1. So we do it in relative to other elements. Then C is a copper, and then S is silver, G is gold, and P is what? Platinum. Don't forget that silver and gold are what we call noble metals. Okay, we explained that in one of our previous lessons. So all of this was now the level of reactivity usually is decreasing. Okay, when it's decreasing, it means that potassium is the most reactive, okay, followed by sodium, followed by lithium, and this one is the least, okay, among them. So as it's decreasing, so this is the highest by this, by this, by this. So if we are going to be looking at from the options, we're giving less than, so which means we are going to be arranging from the smallest. Eventually platinum is going to be lesser than gold, which is AU, lesser than silver, and so on and so forth. But we don't have all of this one in the questions, okay? So this is just to help us. So let's look at the options. The options we have now, we have AU, we have CU, SN, FE, CA. Like we have the same elements that are daring, but they are what? Changed all over. So we'll just write the elements that we have, then we arrange them. We write the elements we have, then we arrange them. We have AU, that is your gold. We have copper, that is your gold. We have Fe, okay, that is your iron. We have tin, That's SN. Then we have calcium. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so let's arrange them now. Let's arrange them in order less than. So that means in order of in increasing order. Okay, so we have AU. Let's start from here. This is the list. Platinum. We don't have platinum here. Gold. Do we have gold here? Yes, we have gold. That is our AU. Please don't forget the symbol for gold is AU. So we have AU is less reactive than, do we have silver there? Silver AG. We don't have silver. Copper. We don't have, okay, we have copper here. CU. Okay. Less than CU. Then we have less than, we have, that's CU. Then we have, do we have hydrogen? No. Do we have lead? PB? No. Do we have tin? SN? Yes, we have SN. So less than SN. Then less than, we have, do we have iron? Yes, we have iron. Okay, that is Fe. Less than Fe. And then the last one, less than Ca is the last one, calcium. Okay, less than calcium. In other words, calcium is the most reactive, followed by iron, followed by tin, followed by copper, and then followed by gold. Gold is the least among them. So let's look at the screen and let's see the options that best fit in with that. We have AU. Option A says AU is less than copper, is less than tin, is less than iron, is less than calcium. This happens to be the correct one. Let's look at option B. It says calcium less than this. There's no point wasting time. We have already seen what we have worked there. So the answer is AU. Gold is less reactive than copper. Copper is less reactive than tin. Tin is less reactive than iron. Iron is less reactive than what? Calcium. So the correct answer is option A. Question number 91. An oxide of nitrogen that can rekindle a glowing splint. Glowing splint, okay? Oxide of nitrogen. There's a gas that also behaves like that, okay? That is oxygen. Oxygen has a characteristic of what? Rekindling a glowing splint. So both oxygen and nitrogen 1 oxide, they behave the same way, okay? They rekindle, they have some things in common in terms of when it comes to rekindling of the glowing splint, okay? The flame that they have actually rekindles a glowing splint. So nitrogen 1 oxide, yes. Nitrogen 2 oxide, no. Nitrogen 4 oxide, no. Dinitrogen tetraoxide. There's no way we might be able to prove this one. You just need to know this one, that the gas, the oxide of nitrogen that actually rekindles a glowing splint is nitrogen 1 oxide. Nitrogen 1 oxide, okay? Like we also have the laughing gas. There's a gas we call laughing gas, okay? So, but that's not our point now. So, an oxide of nitrogen that can rekindle a glowing splint here is nitrogen 1 oxide. So, the correct answer is option A. Now, let's move on to question number 92. In a chemical reaction, surface area of reactants can affect what? Surface area, don't forget, surface area tend to affect the rate of chemical reaction, okay? When we talk about surface area, we are looking at the substance, most cases, solid substance, okay? When you bring in a solvent to react with it, if it is in powdery form, the rate of reaction is going to be faster. If the same substance is in solid form, okay? Let's say in grains, okay, or in pellets, the rate of reaction is going to be slower compared to when it is in powdery form, because the powdery form, the particles are fine, okay? They are fine. The particles are very tiny and small, so there's going to be a larger surface area. So when you have with the reagent or the solvent that is added to it, what happens? All the particles will begin to what? Will come in contact with the solvent you are adding to it. So the surface area is larger, then the reaction will be faster. If you look at option A, says calcium carbonate plus HCl to give us calcium chloride plus H2O plus CO2. Of course, this calcium carbonate is not in liquid form. Usually it's in solid, like your limestone. You see the way it is in granules, okay? And then in those particles, when you bring sodium HCl, hydrochloric acid, add it to it, what happens? Of course, there's going to be, you will see the gas CO2 that is being given off, and then there will be dissolution of that calcium carbonate, okay? So once that is happening, all of the surface area of that reactant will be affected because the particles will come in contact with HCl, and then we have that. So surface area of this reactant, especially this one, okay, in this chemical reaction can be affected in this one. For option B, we have magnesium chloride. We can have magnesium chloride in aqueous form, okay, if it is dissolved already. So if this one is in solution, for instance, or in aqueous form reacting with another aqueous form. Of course, the reaction is just the way it is. We don't have any solid substance there. Okay, so this cannot be affected by surface area because it's possible they are in the same state, even though the state is not shown here. Then H2 and Cl, this is gas, gaseous reacting together to form this hydrogen chloride gas. Okay, when you form the two of them, this reacts with this. Don't forget we are looking at what the reactants, both of them in gaseous state. Surface area does not have any effect on this. For this one, we have, this is aqueous, this is what? Aqueous. Surface area does not have effect on it. When we talk about surface area, we're talking about solid substance. So usually when limestone reacts with hydrochloric acid, limestone, which is solid state, you have this, you have this, you have this. So surface area has a role to play in this because it makes the reaction faster. If they are in powdery form, the surface area will be higher, and then there will be contact between the limestone and the hydrochloric acid. All the parts will be reacted, finally. So in the chemical reaction, surface area of reactants can affect calcium carbonate plus HCl to give this, and this. So the correct answer is option A. Question number 93. C2H4 plus O2 plus CO2 plus H2O, okay, is balanced stoichiometrically, okay, gives this and this. So the reaction is actually, they are all gaseous, in gaseous states. Of course, this is a combustion reaction, a reaction of hydrocarbon reacting with oxygen, okay, to produce CO2 and water. That's what complete combustion of hydrocarbons will always be. We always form CO2 and water. If you react methane, CH4, with O2, you will still have CO2, and if you react propane with O2, you will still have CO2 and H2, but you need to balance up the equation. Now, the above equation represents the combustion of ethane. If 10 cm3 of ethane is burnt in 50 cm3 of oxygen, so this is the amount or the volume, okay, of ethane that is actually required to react with 50 cm3 of oxygen. So what would be the volume of oxygen that would remain? So we want to have the residual volume that we want to have. So before we find the residual volume, first we need to know the total number. We're given the total volume that should react, and then the one that we will now find the one that is reacted, okay, that reacted in this reaction. Then we'll subtract the one that reacted from the total volume, okay, that was required, and then whatever thing we have is going to be our residual volume, and that gives us the answer. So let's move on to the board now. We have the equation here already. That is your methane gas, that's your ethane gas reacting with oxygen, combustion to form that. So if you look at the combining ratio now, according to Gay-Lussac's law, okay, that says that provided temperature and pressure remains constant, when volume reacts, when gases react together, they do so in simple whole number ratio, okay, that bears so in that. So we have, this is ratio 1, of course this is 1, so this is 1 mole and then to 3 moles. That's what we have. Then to produce 2 and 2. So since the reaction between ethane and oxygen combustion, so we can say this is the number of moles. The mole ratio is ratio 1:3, okay. And then if that is it, what is the total volume that is required? Total volume required in this reaction should be what? We're told that 10 cm3 of ethane. So that means we need 10 cm3 of ethane is what is required to take place in this reaction to react with 50 cm3. It's there in the question. 50 cm3 of oxygen, okay? That is what is required of us. That for this reaction to take place, we need 10 cm3, we need 10 cm3 of ethane, and then we need 50 cm3 of oxygen for that combustion reaction to take place. But we discovered that what reacted actually was what? Reacted volume. What volume actually reacted, okay? We can get that according to Gay-Lussac's law. If 1 mole is in ratio, the reaction is between ratio 1:3, and then the reacted volume will be what? We already know that the volume of ethane is 10 cm3. So if the volume, of course, is 10 cm3 in ratio 1:3, and if here is 10 already, what will this be? Of course, it's going to be what? 30, because in ratio 1:3. So we just multiply this by 3. If 1 mole give 3, then 10 will give x. Okay, so 10 times 3 will give us 30 cm3. So which means that the mole the way they reacted in volume also is in that reaction. So the total volume required was told us in the question that 10 cm cube, okay, of a tin is required to what? To react with 50 cm cube of oxygen. But we discovered that based on the what? On the stoichiometry, based on the what? On the mole ratio of the reaction where we balance, we discovered that the reacted volume was just 10 cm cube of this 18 and then just 30 because it is ratio 3, 1:3. So that means 10:30. If you cancel 10 by 3, you still get 1:3 back. Okay, so that is ratio 10:3. So when we have this is the total and this is what reacted, so we can get the residual, what is remaining. Okay, so residual volume now, which was what we were asked to find, will be what? Of course, you can subtract 10 minus 10, that gives us 0. So that means all of the 18 is used up. There's nothing that is left again. Then we have this 50 minus, of course, 50 minus 30. That gives us what? 20 cm cube. So which means the residual, we still have, this is not used up. You know what we call, in every reaction, we have what we call limiting, reagent. Okay, there's one that is used up, there's one that is remaining. For here now, we can see that the whole of this 18 is used up completely, but we still have 20 cm cube of oxygen that is left. Let's go back to the screen and see the options we have there. So option A says 20 cm cube. Yes, of course, that's what we had. Option B 40, option C 60, option D 50 cm. So the correct answer is option A. Now let's move on to question number 94. The hybridization scheme in ethine, don't forget ethine is an alkyne family, okay? They have CnH2n-2, okay? The hybridization scheme in ethine, hybridization has to do with just binding together, okay? Coming together, combining two orbitals together, two or more orbitals together, whether the s orbital, the p orbital, the d orbital, okay? Or the f, so as the case may be. So we can have sp3, we can have sp2, we can have sp, we can have sp3, D, we can have sp2d, we can have sp2, and so on and so forth. Those are hybridization. So when you have the orbitals that are combined together, two or more orbitals combined together, we call hybridization. So the hybridization for this scheme, for ethine, is what? Is it sp? Is it sp3? Is it sp2d? So what happens is that, in ethene we have two carbon atoms there. So one of the carbon atoms, okay, one of the two carbon atoms there, we have 2s, the two carbon atoms have 2s orbitals. So one of the 2s orbitals from that carbon atom, okay, is going to combine with the 2p orbital. So when they combine with the 2p orbital like that, what happens? That is now going to generate the sp orbital. So we are going to form sp orbital because the orbitals will be far apart from each other and then going on a straight line, okay? So that is between them now. That angle going on the straight line gives us the sp orbital. So one of the two carbon atoms that we have, one of the 2s, okay, will react or we add up to or we hybridize with the 2p orbital, okay, just one 2p orbital. So one 2s, one 2p gives us what? One sp. So we'll just have the sp orbital. So the hybridization scheme in ethine is actually sp, not sp3, not sp2d, not sp2s. The correct answer here is option A. Do you have any question bothering you at all? Please feel free to ask your question. All you need to do is to click on the link in the description below that takes you to the Myschool website. There you'll be able to ask your questions and solutions will be provided within the shortest period of time. Now let's move on to question number 95. An organic compound with general formula RCOR prime is an what? Of course, is an article because all of them start with letter A. With an alkanone, with alkanal, with alkanoate, with alkanoic acid. All of them sounding the same. Alka. Okay. So usually we know that alkanone, okay, are your ketones, okay, and they have the formula. We have the RCO. Let's see if we can write them. Let's see for that. Then we have okay, we can have R prime here. Of course, that has already shown what the answer is. The alkanal has this ROH, okay, that's the general formula, the OH group. Then we have the alkanoate. Alkanoate we have R. COO, you can see that, not CO, COO, then we have R prime. There's difference between this and this. There are two oxygen molecules here, there's just one here. Then the alkanoic acid, we can have RCOOH, okay? Yeah, so these are the general formula for each of them. So I think this one explains and can tell us what the right answer is. So an organic compound with general formula RCOR prime, the R can be a methyl group, let's say CH3, and then here can be CH2, 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 CH3, and so on and so forth. So it can vary, and it could even be the same thing. So the correct answer here is option, because this is already what is matching with this. So the correct answer are your ketones, okay? So it's the alkanone. So the correct answer is option A. Do you have better steps or better explanation to some of these questions that we have solved? Please feel free to share. All you need to do is to go to the comment section, indicate the question number and the answer you wish to share. Now let's move on to question number 96. The amount of Faraday required to discharge 4.5 moles of Al3 plus aluminium ion is what? First, before you solve this, we have to write an equation, okay, to show the dissociation of that aluminium ion. So we have Al3 plus, okay, Al3 plus is going to lose 3 electrons to actually, before we have aluminium metal, okay, so which means we have 3 electrons. So, and don't forget that 1 mole, yeah, is actually equal to 1 Faraday, okay, but in this case now, we have 3 electrons here. Also recall that the 1 electron is equal to 1 Faraday, okay? So that means 3 electrons will be equal to what? 3 Faraday. So we can say that 1 mole, therefore 1 mole will be equal to 3 Faraday, okay? So if 1 mole is equal to, of aluminium is equal to 3 Faraday. Now we're asked to find how much of the Faraday is required to discharge 4.5 moles. So if 1 mole gave 3 Faraday, then 4.5 moles will give how much of Faraday, okay? So if you do your cross multiply, we have 1 times x, that is x, then we have 3 multiplied by 4.5. If you multiply that together, we're going to have that is 13.5 Faraday. So X is that. So the amount of Faraday required to discharge 4.5 moles of aluminium ion is, let's move to the screen. Option A is 13.5 Farad. We have 4.5, 7.5, 1.5. So the correct answer is option A. Question number 97. The reaction between alkanoic acids and alkanols in the presence of an acid catalyst is known as, this is also a direct question, okay, it's a bonus mark and a straightforward question. Reaction between alkanoic acid and alkanol, usually we give you alkanoate, or what we call esters, okay, in the presence of an acid catalyst, okay, you form esters and water. So if alkanol, for instance, let's say ethanol, reacts with ethanoic acid, okay, we are going to have ethyl ethanoate, that is our ester, okay, or our alkanoate plus H2O water, and the process is referred to as esterification. So option A says saponification. Saponification is the process of soap making, okay, alkali, hydrolysis of alkali, okay, or fat and oil. Usually fat and oil react with alkali, let's say sodium hydroxide, you form your soap, that is saponification. Option B says dehydration. When you remove molecules of water, okay, that is what dehydration is from a particular substance, and that's not happening here. The reaction is between alkanoic acid and alkanols. Option C says esterification, which is correct. Option D says hydrolysis. Actually, the reverse reaction, okay, is what we call hydrolysis, or between alkanols. You know, alkanoic acid reacts with alkanol to form esters and water. So if you reverse the equation and say ester plus water to give alkanoic acid and alkanol, that is hydrolysis, okay, of which is not it. So the correct answer here is option C. Question 98. The reaction CX C subscript X, H subscript Y, O plus 5O2 will give CO2 and water, okay? The question says CX, H subscript Y, O in the equation is what? So all the examiner wants us to do is just to balance the equation, and then we find out the compound that we have on this point. So if you can balance well, and then we are good to go. All you need to do now is we look at the number of carbon on this right hand side to make it easier, okay? It must reflect on this carbon here. The total number of hydrogen here must reflect on this hydrogen here, and then the number of oxygen that we have on the right hand side must be the same as what we have on the left hand side, and then we are good to go. So let's have carbon. We have 4 carbon here, 4 carbon atom on this point. So let's move on to the board so that we can see what we have here. Okay, so we have 4 moles of carbon here. So that means 4 must be here too. So we must have C4 here. Okay, then H. Let's see hydrogen on this right hand side. 4 times 2, that is 8. So we have 8 moles here. Let all the 8 also be here. It must reflect there. Then oxygen is the last one that we have here. So first, let's look at the total number of oxygen we have on the right hand side. Must be the same with what we have on the left hand side. So this is 4 times 2 here. That is 8 moles of oxygen here plus 4 here times 1. That's 4. 4 moles of oxygen. So by the time you add up together, you have 12 moles of what? Oxygen that we have on the right hand side. So on the left hand side must also have 12. So this is 5 times 2, that is 10 moles of oxygen already. So this is 12, this is 10. So we are left with 2 here. So which means the 2 will belong to this what? Oxygen here. So we have C4, H8, and then O2. But if you look at the options we have, we don't have C4, H8, and O2 there, okay? So the next thing you need to do is what? Do we have any common factor that can go in here? Yes. 2 is a multiple of each other. So if we divide this by 2, divide by 2, divide by 2, so we are going to have C2, H4, and then O1, okay? That is O. So C2, H4, and O. So this is the compound that we have. So let's move on to the screen. Option A says CH2O, no. C2H6O, no. H4, C4H, then C2H4O. So the correct answer is option D. Now let's move on to question number 99. Alkylation of benzene is catalyzed by what? Alkylation of benzene. That reaction is just a reaction that has to do with addition of alkyl, okay? Like we have alkylation, okay? An alkyl group which could be Al, represented with Al, maybe CH3 or C2H5, C3H7, and so on. So when any of the alkyl group is added up to benzene, okay, we are going to have what we call an alkyl benzene, okay? It could be methyl benzene, or it could be, ethyl benzene, as the case may be. So addition of that, but that reaction is going to take place in the presence of a catalyst, okay? Catalyst, and usually the catalyst that we use, we call it the Friedel-Crafts, okay? That is the catalyst that we use, and that is no other than aluminum chloride, which is option D, okay? Not palladium, not nickel, not sunlight. Don't forget, catalysts are specific in reaction. You don't just say, okay, if I don't see this, let me use this. No, catalysts are specific in reaction, okay? They speed up the rate at which the chemical reaction take place or occur. So alkylation of benzene is catalyzed by aluminum chloride. So the correct answer is D. Question 100. Benzene formed nitrobenzene at temperature of 60 degrees Celsius when it reacts with mixture of concentrated triazonitrate 5 acid, that's the nitric acid, and concentrated what? Is it phosphoric acid? Is it hydrochloric acid? Is it tetrazoline sulfate 6 acid? Is it hydrogen iodide? Let's look at the diagram. Don't forget that your benzene is, according to Kekulé, you can have it drawn this way, either this way, or we just draw it like this. Double bond, single bond, double bond, single bond, double bond. That is a benzene. So whichever one you wish to. So for the sake of this, I will just use this because of the reaction that we want to have. 6-sided, then we have a ring in it. Okay, so benzene usually we react with nitric acid. We have, is the mixture, not just one of them, HNO3 and concentrated H2SO4, that's the sulfuric acid, then you are going to have what we call a nitrobenzene eventually. We have, that's our color, then we have your NO2 at this point. If you like, you can have it this way, double bond oxygen, as the case may be. So this is your nitrobenzene that we have in here, and the temperature is at 60 degrees Celsius. That's very important. Nitrobenzene, we have a benzene here reacting. Don't forget your benzene is C6H6, okay? Then reacting with nitrobenzene. So nitrobenzene is going to be C6H5 because one hydrogen has been replaced by this NO2. So this is the formula for nitrobenzene, and then we have this. So this reaction will take place at a temperature of 60 degrees at the condition that nitric acid reacts to a sulfuric acid for us to have a nitrobenzene. So let's move on to the screen. The options is sulfuric, these are the tetrasulfate 6 acid. So the correct answer is option C, tetraoxosulfate 6 acid. I believe you enjoyed this content because I really had fun solving these questions. If yes, please don't forget to click on the like button, hit the subscribe button, and finally tap the notification bell to keep you informed once we upload our next video.